Hello everybody, welcome back. In this video we'll be talking about elasticity, which is the property of materials to respond to forces, to stresses, it's another word that we'll define just now, with deformations. And this is the natural continuation of that journey from extremely idealized, namely a single, so treating objects like point particles. We now understand that actually objects are extended, and therefore it's no longer enough to just describe, the forces F1, F2, and so on that act on these objects, but also that the placement of these forces, namely the point of application, matters, and they have different effects according to where they are applied. And so we defined torque, and now you're starting to understand a little bit and practice on how that applies to the equilibrium of objects. And the next step up in getting more and more refined and more accurate in describing reality is understanding that actually when you take an extended object and you apply a force, typically this extended object, this object will deform. If I pull a piece of Play-Doh in this direction, then typically this object will stretch a little bit. If I compress it, let's change color. If I push inward, then typically this will result in a compression of this material. Elasticity is the situation or the theory of elastic materials, and this means that we're talking about those situations where deformations then go back once or vanish or disappear, let's say, disappear when the stress or the force is removed. This is as opposed to instead something we won't be talking about, but you may encounter in your future, which is plasticity. Plasticity, which is where the deformations remain. Deformations remain. So if you ever wondered what the key difference, at least in scientific lingo, is between elastic and plastic materials, elastic materials means that their deformations go back to zero. The shape and size go back to normal once I remove the force, the external force, whereas plastic materials, I can reshape them, or it's the effect where they get reshaped. Okay, very nice. So you may wonder, why elastic? Okay, there's something about, bounciness or that suggests elastic, but we have used in physics elastic in a very specific sense. Namely, let me clear out. We use elastic to describe this law. Let's just use K, where the elastic force is K times displacement. If you have a spring, this is well known, certain equilibrium position that I tend to define to zero. If I displace, to zero, if I displace this the spring by a certain delta x, then the force that the spring exerts on me is precisely K, the spring constant, times delta x. As it turns out, this is also the way in which elastic materials respond to deformation. So elastic materials respond to deformations in this way. Exclamation mark. This is surprising and interesting and awesome because we know, well, you know how to deal with, springs and pendulums, for example. It's the same type of behavior. And one of the things, for example, that I'm sure you remember is that the energy stored in a deformation or a displacement like this is 1/2 k delta x squared. So this creates, you already have the language essentially, or the machinery to deal with the changes of forces, accelerations and whatnot, and the energy stored in elastic processes. We just need to apply them to actual materials and see what that looks like, not for just, a spring or a mass attached to a spring, but for real materials. All right, let's get started. Let's say that I have an object. Let's, just for the sake of it, let's draw it like a bar of, I don't know, whatever material, some material. And let's say that you apply on this bar a force downward, well, in this case downward, apply on this surface, on this face, which has area A. All right. The object has, when undisturbed, has a length L naught, so that's the undisturbed height in this case. And you can probably imagine if you squeeze, or if you pinch between your hands, a little stick like that, or in general, like if you apply a force like this one that I drew, you can probably have the intuition that this will decrease a little bit in size. So after this compression, the object has actually shrunk to this size, for example. All right. So compressing by a certain delta L. Let's define a couple notions, a couple objects that we'll start using this week. The first one is stress. Not the psychological stress of having to deal with me as your lecturer and with mechanics as a course, but in physics and engineering, we call stress the ratio of force and the area over which it is applied. Typically, this is denoted with sigma, the Greek letter sigma. You may find other letters, but this is pretty standard, I think. And so what are the units of stress? Well, it's the units of a force over the units of an area. So in SI units, let me put square brackets to be clear. In SI units, this would be Newton over meter squared. And there's a specific name for this, honoring the French scientist. It's Pascal, or PA. Another one of those cases where famous scientists gave their names, or we gave the name of a famous scientist to a specific unit, like Newton and Watt and Joule and so on. Okay, now what else? We can define strain, again, not the psychological strain of dealing with me, but the physical strain, typically denoted with epsilon. This is another one of the Greek letters, epsilon. And this is the relative or percentage change in the length of the object, or in this case, the height of the object, right? So these are two convenient quantities that I can define to describe what is happening here to my stick on the left-hand side. And the interesting and very useful relationship that these two quantities, stress and strain, have in the elastic regime is that they are directly proportional to one another. And in particular, we have this relationship that says that sigma, the stress, is proportional to epsilon, and the proportionality constant, very unfortunately typically called E or Y, capital Y, is called Young's modulus. Modulus. Very important. So another way of writing this, let me put a block around it. Another way of writing is, there's a couple very clever way actually to rewrite this, and it's clever, maybe it's a bit of an overstatement, but interesting ways to rewrite it that illuminate some of the properties of this relationship. So what this means is, let's write it again, that F equals F over A, so the force applied over a certain area is equal to delta L over L naught, the strain, so the percentage variation in the length of the object, times this constant, that's the Young's modulus. I just rewrote this essentially in spelling out the stress and strain. And this also implies that the strain is equal to the stress divided by Young's modulus. And look at this. This means we can read several things from this relationship. First of all, what is the physical meaning of Young's modulus? Well, a large Young's modulus means that it's really difficult to achieve a large strain, so significant changes in the size of the object. So in a way, the Young's modulus is the ability of a material to resist changes in length, so stretching and compressions in length. So a stiff material would have a large Young's modulus because it takes a lot of force or a lot of stress, rather than force, to achieve a certain percentage change in the length. In the other way around, a soft or a malleable material would be one where Young's modulus is relatively low. So it doesn't require a huge stress to achieve a certain strain. Another way of seeing this equation, let me clean this up again, is that if I apply a stress that is a certain percentage of the Young's modulus, let's say 1% of Young's modulus, I'm compressing, well, formally speaking, compressing or stretching, depends on the direction I'm applying the force, by the same percentage, 1%. So the Young's modulus gives you immediately an order of magnitude for a stress that results in a significant or a tangible change in the size of the object. So that gives you immediately like a ballpark value for, hey, if I need to change, either elongate or compress a certain object by a certain percentage, what kind of ballpark stresses am I talking about? And Young's modulus is precisely that ballpark. Again, if you need X percent of strain, elongation or compression, you need X percent of the Young's modulus to achieve that. Nice. Let me shrink all this and put it over here. Somehow this got left out. Let's just delete this. And let me spend 1 second trying to explain to you or to reveal why all of a sudden, or where the elastic analogy or the elastic relation comes from. And it's the following. So another way where I can write this relationship, where stress is equal to Young's modulus times the strain, or F over A is equal to a constant, Young's modulus, times delta L over L naught. I'm going to rewrite this as F equals, look at this, Young's modulus again, area, so the surface area over which I'm applying the force, the original length or height of the object times L. And if I just take this combination, Young's modulus area over length, and I call it K, I'm back in the situation where I have precise, oh, this is not L, but delta L, pardon. Apologies, delta L, K times delta L. This is the good old Hooke's law. This should be Hooke's law that you all know and love and can use very happily. This is where the elastic analogy comes from, really comes from, and where all the power of what we used for springs and pendulums all of a sudden can be applied to an actual physical, real material that is being either squished or elongated by a certain stress. Really, really powerful stuff. Really, really nice. We mentioned the energy stored in this deformation, and we said that the energy, let's call it, E. See, this is why E is so unfortunate, because I would love to use this for energy, but let's use potential energy stored in this deformation, then is 1/2 K delta L squared, or 1/2. K is this combination where it's E A over L naught, and then delta L squared. So if you ever wonder, compressing a piece of material by a certain delta L, how much energy then can I utilize as a result of this to do some work, or to exchange energy in a different way? This is the value of energy that you have available. All right. And we can use all the language of energy conservation, work energy theorem, and all of that stuff. Again, very, very nice. Next up in the types of deformations that we can apply on an object is shear. So let me try to draw this picture as well as I can. Imagine you have a parallelepiped like this that is glued to a tabletop. So the bottom surface, the bottom face is held fixed like this. And let's say that this object has height h and has a cross-sectional area A, like before. And in the case of stress and strain that we talked about, there was an external force applied perpendicular to this face, either up or down, causing a change in the height of this object. When it comes to shear instead, we consider a force that is applied perpendicularly to this face. Okay? And so you can probably imagine that the resulting deformation is something like this, where the face that I'm looking at goes from being a rectangle to being a parallelogram, slightly tilted parallelogram. And in particular, this delta x is quantifies the amount, the change in shape. So the new key quantities that we define are shear stress, which again is the ratio of force and area, so the same units as before, Pascal or Newton over meter squared, or Pascal, and the shear strain, which is no longer delta H over H, which was the linear strain we talked about before, but it's delta X over H. So shear is basically the transverse, the reaction of a material, the response of a material to transverse, to perpendicular forces, perpendicular to the surface that I'm considering. And so how much this surface is displaced, in this case horizontally, over the original height of the parallelepiped, that is the shear strain. Interestingly, we again have a linear relationship between these two quantities, the stress and the strain of shearing. And in particular, we find that for shear, the proportionality constant is called G. And I'm very upset about this. Very poor choice, because we already have it for, well, actually Gibbs enthalpy, but also Newton's constant that you've seen last week. And sometimes, to make things even more confusing, so this, by the way, is called the shear modulus. And sometimes also known or denoted with S, or sometimes, to make things even more complicated, sometimes denoted with mu in different contexts. I'm going to try to use G as much as, and to be consistent with that, but apologies for that. I don't make these rules. And yeah, so again, even in shearing type of deformations, we have a linear relationship in the elastic regime between the shearing stress applied and the shear strain that this stress results in. Very nice. And last but not least, you can think of an object, for example, when you immerse a balloon in water, or in a pressurized tank, where let me draw it maybe as a sphere, and where there's a pressure applied uniformly to this object in all directions. And this pressure, again, is essentially the volume equivalent of the stresses that we talked about. So it's, again, a force per unit area. Okay, pressure. And you can probably imagine, if I squeeze, or I mean, it could be a negative pressure, so it could be, the forces could be going in the opposite direction, and you can probably imagine that this will result in a sort of in a squeezing of this object. And the changes that I'm interested in is not so much this distance, but is the change in volume, and in particular the relative change in volume. And so there's the key quantities are then pressure, or volumetric stress, if you want, and delta V over V, the percentage change in volume, or volumetric strain, as it were. And again, these two are proportional to one another. And in particular, pressure is equal to delta V over V times a constant. And there's actually a minus sign. And the reason there's a minus sign is because, let me write it here, it's because a positive pressure implies a negative change in volume, because it's the volume shrinks, so delta V is less than 0. You will find this also expressed with just B times delta V over V, where it's actually implied that delta V is, I'm taking the absolute value of delta V. So as long as you promise not to use this form and misinterpret it as a positive pressure results in an expansion, then you're free. I trust you to use to not use the minus sign, and it's fine, okay? But you need to promise. What is this constant B? This constant B is called the bulk modulus. Again, the same units as pressure and same, so Newton over meters squared or Pascal again. And again, it has the same role as we talked about for Young's modulus for linear strain and for the shear modulus for shear strain, where it gives you a good ballpark for what type of pressures I need to apply to an object to change its volume significantly, and with a precise relationship of 1%. If you apply a bulk modulus, a pressure of 1% of the bulk modulus, you are causing a compression, a change in volume of 1%, right? And so this bulk modulus is how hard this object resists changes in its volume. As it turns out, sometimes the quantity 1 over b is also reported and considered, and this is called the compressibility. Compressibility. Oh my word. Apologies for the compressibility. The reason being that a large value of b, bulk modulus, implies sort of stiffness, or that it's hard to compress an object, whereas a large value of 1 over b, it's the vice versa. So it means high compressibility. It's easy to compress. All right. And finally, there's a very, very neat and interesting relationship that tells us that not only all these formulas that I gave you are valid in elastic materials, but that these new quantities, namely Young's modulus, the shear modulus, so Young shear modulus, and the bulk modulus, are actually related to one another. They're not completely independent. And the relationship that they have between them goes like this, where Young's modulus is equal to 2g times 1 plus nu. This is the Greek letter nu or ni, depends on how you want to pronounce it. And also equal to 3 times bulk modulus times 1 minus 2 ni. So, there's obviously a new name for this nu or ni, which is called Poisson ratio. And Poisson's ratio tells you it's a dimensionless number. Dimensionless. So it's a pure number without units. And it basically tells you how a material responds to certain stresses, but in the opposite direction. Something like, if I draw again the picture that I had at the very beginning with, a stick or a bar that is being compressed down, Poisson's ratio tells me by how much this stick sort of tends to fatten in the middle. Or the other way around would be, if you take a stick like this or a bar or something that's elastic and you stretch it, like when you stretch an elastic band or something, there tends to be a thinning in the middle. It tends to get thinner. So this type of phenomenon is captured by this Poisson's ratio. And somehow, in this very interesting and weird way, it enters in the same microscopic phenomena that macroscopically, so in a larger sense, they create this wonderful relationship between Young's modulus, which is how an object responds to strain, to being compressed or elongated, shear modulus, which is the perpendicular type of shearing stress, and the bulk modulus, which is an overall sort of pressure type compression or expansion. Very, very interesting. This is really, really cool. Nice. To conclude, I want to talk to you about the big elephant in the room, which is when is this stuff valid that I just told you about. So we won't go into too much detail about the microphysics behind or micro material science behind these relationships, but at least I want to give you a sense of the validity of these relationships. And so if we draw a plot between strain and stress applied, this is very, very creatively known as the stress-strain diagram, what we find for a large variety of materials is that there's a more or less linear behavior for relatively low stresses and strain, and this is precisely the elastic regime. This is where all of these beautiful things that I told you about today are valid, okay? However, if you keep going with applying bigger and bigger stresses, then at some point there's a bend, and this happens when I reach this point. That's called the yield strength, past which basically the material starts yielding. It gives in, okay? And then there's, so you see here the material then reduces the resistance, or it keeps it steady as it's straining further. And after this, it picks up again if you keep pushing more and more, reaching some maximum possible value. And this is called the ultimate strength, which is the maximum strength or stress that a material can withstand before failing or before eventually fracturing. So at some point somewhere here, then there's fracture, where a material actually breaks. Fracture, breaking point. So after the elastic regime, there's a plastic regime where past the yield strength but before the ultimate strength, the deformations are permanent. The material will never go back to the original shape and properties, but not yet reaching complete failure. And then after, instead, I get to, and by the way, this phase here is called hardening as well. After the ultimate strength, then there's a phase of necking, as it's called. I'm not going to ask you to remember these necessarily, but just so you know, this is called necking. This is like what you observe in, I'm trying to think of an example, but if you, an elastic band, before it breaks, it starts really thinning into a neck in a specific point where, micro imperfections or weaknesses of the material are more important. You see it, for example, in when you pull the caramel in a Mars bar, you keep pulling. At some point, it forms like a really thin neck at a specific point, and that's where it's going to break. So that happens after I've applied a bigger strain, bigger stress than the ultimate strength, and right before fracturing, right before failing or breaking of that material. Okay, so again, to re-emphasize what we're talking about, most materials have a phase, a regime for comparably low stresses and low strains where I am in the elastic regime, and I can use all the beautiful and simple physics and mathematics of Hooke's law and the likes. And then there are phases where you reach a point where the elastic regime completely fails, and already here it's a bit, it's not extremely precise, where you enter the plastic phase, and then finally, if you keep stressing, then the material breaks, and that's life. All right. Okay, long video, so thank you for your patience. Thank you so much for watching, and I'll see you soon.